for creating a part and doing your simulation. First, we need to define a part. We double click on the part in the tree, and you can take your part as a 3D or 3D planar or axisymmetry, and different types: deformable, discrete, rigid, analytical, rigid, or polarium. For example, in forging or deep drawing, for the die or punch, we take discrete rigid because we assume we don't have any displacement and deformation in die. But for the part, we need to define deformable. Or for example, you want to simulate a bar, we need to take a deformable part. And we have a different type of feature creation. For example, extrusion, we define a section and extrude the section. Or we want to revolute something. We have axis, define our section and revolve section, or we have solid. Now we take solid, extrusion, and deformable, and continue. We have approximate size. With approximate size, you can take and define your sketch size. We take 100, continue. We have a sketch part here, different icons, and we take rectangular and create our part section and dimension it. For example, here 10 and here 5. Now we have our section. If you want to already for complicated part to make it easier to assembly or another things, you can define also the axis to help you for next module, for example in assembly or interactions. And here you can define constraints, for example coincident, axisymmetric, fixed. First we fix the axis. Down, and another axis. Down. Now we have two axes, and we can make this part symmetric according to our axis. Take a axis of symmetric and our entity to this one and symmetry about this one. Now our section is symmetric according to y and x axis. After that, the section is finished and down. Now you can give the depth of the part. For example, 100 and okay. Now we have our part. After this part, this section, this module, we have a property module. We need to define our material properties. In the first one, we create our material properties. For example, here we can define different kind of properties. For example, density or another things. In mechanical, we have a elastic properties. For example, Young module. megapascal and Poisson ratio 0.3. Abaqus is the dimensionless software. When you take, for example, megapascal as a unit for the Young module, your dimension should be millimeter. Or when you take, for example, density, your unit should be ton/hour millimeter cubic. Or if you use normal ISI, the density is kilogram per meter cubic. Or your Young module should be in Pascal, not megapascal. That's very important. And after that, we can define plastic properties according to the stress strain curve. We can give our data. For example, you have lots of data, you can copy and paste directly from Excel to this table. And first yield stress should be, first plastic strain should be 0 in the plastic properties. That's very important. If you don't take, it will make error. Here we just take two data. That's enough. After defining the material properties, we should define a section. Create, and we have different sections. In the part module, if you remember, I take a solid, 3D solid. When your section is 3D solid, here also you should take a solid. Or if in the part section you define a shell, here you should take shell. Here now we have solid, and we assume this one as a homogeneous, and continue. And you can see here the material name, material 1. Here we can change the material, for example, steel. And here, section 1, for example, solid homogeneous, continue. See here, the material name is steel, as I renamed. Okay, and we have a beam section, solid, type of solid, and homogeneous. After that, we need to assign this section to our part. Maybe in one part you have different parts. For example, you have 2 or 3. You should define for every part individually your sections. For example, for the shell part, you define shell. For the deformable, define 3D homogeneous solid. And here we assign to the part. We click on this one. We take your part and down. The section is beam, and the material is steel, as you can see here. And okay, the color change to the green. And this section and this module finish. Next module is the assembly. We should create your instance. Here we have 2 important options, dependent and independent. Always we take dependent because we want to mesh each part individually. So that's okay. Okay. Assembly is the necessary part for all of the CATIA's Abaqus models. After assembly, if you have 2 or 3 different parts, you should call each parts individually and assemble them together. You have different constraints here. For example, parallel face, face-to-face, parallel edge, and you should take a suitable constraint. And as you can see in the tree also, we have part, and see here, position instance now is empty. If we have 2 or 3 different parts, position constraint will be full. After assembly, we have a step. Here we define our steps. Initial step is by default. We have an initial step by default for all the models. After that, we create. You can see we have different kind of steps. For example, dynamic, explicit, or implicit, and solid general. Now we take just static general and continue. Here we have different options for the steps. For example, we have a null zone part here. Now that's off. If you on the null zone part, your simulation will be done non-linear. If we off it, we will just have a linear simulation. Now we take it off to reduce the computation time, and okay. Now our step created here. Static general null zone is off, and the time is 1 second. After a step, we have interaction, because here just we have one part, we don't need for interactions. In interactions part for the multi-part models, you can create your interactions here, create, and we have different kind of interaction. Surface to surface, self-contact, model change, and other things. Like material properties module, here also we need to follow same procedure. Here, for example, we define our contact properties. For example, contact, continue, and mechanical. You can see the tangential behavior, normal behavior, or another behaviors. Now we don't need for interactions. After interaction, we have a load part. Here we define our boundary condition and our load. First icon is the load, second one is the boundary condition. First, we define a boundary condition, create, and we take first one, symmetry. That's depend on your simulation. You can take any of them depend on your simulation. Now we need first one. Continue, and I'm going to fix the end of the beam. I fix it and down. That's fixed in all directions, in rotation and displacement. I take the last one, and okay, now our beam is fixed. Boundary condition is okay. Here we have a load part. We are going to create our load, create, and you can see different kind of the loads. For example, pressure, moment, and any kind of load depend on your simulation. We take first one, for example, concentrated force, continue, and now we need to define a region. I take this point down. This is the force in X direction, this is in Y direction, and this is in Z direction. In X direction is 0, or in Z direction is 0. In the Y direction, for example, 1000 Newton. And okay, now our part, we can see in the part our load created. And the load module also finish here. After that we have a mesh part. In the meshing first you need to define your global size or seed mesh size. For in first icon, as you can see here we have two different kind of object, assembly and part. If you remember, in assembly I take a dependent mesh on part. Now I need to take here part. You can see part, assembly. For assembly, that's impossible because I take in the assembly part as a mesh on part. So here also I need to take part. I take part and seed the part, approximate global size. That's your mesh size. For example, here we can take one. And different kind of control you have. For example, if you have a curve, you can decrease this one to, for example, 0.05 to increase your accuracy in simulation. Now we don't have we don't need for that because we don't have curve, so 0.1 is okay. And our part is sealed. After that, we have a mesh section. I mesh the section. Okay to mesh the part? Yes, and our part is meshed. Now you can see the number of elements here. 5,000 elements created for this part. If you take a full line, so I decrease the number of mesh with increasing the global size. Okay, that mesh. Now we have 40 elements. I increase the global size and subsequently the number of elements decreases. Here also we have another important icon, assigning element type. Here, as you can see, we have standard and explicit. If your simulation is explicit, that's important to take explicit one. Now our simulation is standard, so we take standard. And your mesh type mentioned here. Our mesh is 8-node linear bridge, reduced integration, hourglass control. That's okay. And there is another options here. Keep them as a default. And okay. After that, we have a job part. You can create your job. This is the model name. As you can see in the tree, the model name is here, model 1, and the name of job, for example. This is the job edition. You can control your job here and keep everything as a default. Okay. After that, we need to submit our job and submit it. As you can see here, job submitted. Submitted. Running. Now the step is running. Completed, right? And simulation completed. Here you can monitor your job. For example, when you submit it, when it completed, the time of completion. If you have any error, you can control your error here or your warning and other things. Here you can visualize your result. Our simulation is completed, and this is the result of simulation. In the table, you can see the legend, the Van Mises stress distribution in this part. And this is the, as you can remember, fix here and load the bar, apply the bar here. And this is the displacement in our bar. And if you want to take any specific result, we have a section here, tool, Aggregate Data Manager. Yes, create XY data. You can see here we have a different kind of output. This simulation by default calculates different things for you. For unique node, for example, we have different kind of outputs. For example, equivalent plastic strain, or reaction force, or stress component. For example, mazes or maximum principles or another. For example, we want to see how much is the equivalent plastic strain in this node. So I take this one, and we need to take element, edit section. I'll take this one down, and we are going to plot the. This is the distribution of our strain. For example, here we don't have any plastic strain. As you can see, in the first frame is 0, and in the second frame is also 0. Or change our variable to the stress component, for example, Van Mises. What you can see here, the diagram, the distribution of the Van Mises stress.
This is linear analysis. So change the option to
explicit.
Yeah, to explicit and non-linear in 10 steps.
In 10 steps.
10 steps.
If we want to change our simulation type, we should back to the step module. In step module, we can replace and change our step. Now our step is static general. We can replace a step as a dynamic explicit. I take dynamic explicit, continue. Here, as a default, null zone is on, so our simulation will be non-linear. We have different options, incrementation, mass scaling, and other. We keep all of them as a default. It's okay. Now our step is dynamic, and static change to the dynamic. Here, in the explicit, by default, we have 20 frame. We can change the number of the frame. Here you can see the interval is 20. As Professor said, I changed this one to the 10 frame. The interval is 10. And here is the your output. If you need any specific output, you can, for example, if your simulation is, you have a thermal change, you can here take a thermal. Okay. All the things is same, just here we need to change our mesh type. As I told you, the part here. You can see the part, the element library that's standard. Now it's necessary to change it to the explicit. Now this is explicit. And you can see here again the name of the name of mesh. Okay. And I create another job. Continue. It's okay. Start. The computation time here is more than standard, and it will take a longer. For explicit, another important thing is defining density for your part. So in material properties, also I edit the part properties and assign density. For example, 2.7 minus 9. This is the mass density of this one also, the load is too much for this simulation, so I decrease the load here.
These steps, you have only one step, so you need to have another step.
Also, I think the problem is with the density. I take it rank.
No, you have to take a ton per meter.
Yes.
You insert already ton per meter? Ton per millimeter.
So that will be -6.
This is 2,700 kilogram, correct?
Yes.
Just take it 2,700 kilogram, E minus power 12. Yeah, just take it like that. This is the question which I asked you. Write 2,700 as it is. 2,700, yes.
Kilogram.
E minus, yes, minus 12. So what is the error?
Density also.
So we think it was millimeter.
Kalau manis tu kita ambil kan patutnya kalau tukar tu kena manis semua. Tadi
The problem was with the dimension of the density. Dimension of density for explicit is very important. As I told you, if your dimension is millimeter, your density's unit
Ton.
should be ton per millimeter cubic.
So what is the value you inserted now? Hello?
Value is so, so 2.7 power E9.
9.
Positive 9, not minus 9. Because the
Sorry, yeah, it will be yes. Because here we have 9, here we have minus 9, we come up, then it is positive 20.
now here we can see our result. The job is completed. Result. We have only displacement in this element. We can
increase the force.
The force. And submit again.
Dia increase dia punya loop sampai 4 minit.
Saya tak dapat ni. This load is too less for this relation.
Macam mana?
Padat ni. Tadi 5,000, next 1,000 tadi tahu
10,000.
Yeah, maybe because of the number of mesh for plastic deformation is very large. So we need to make it more small. Okay, anyway, yeah, this is the wood really started like you. Okay, yeah, we started together. I gave him the fundamental course and he used the software, and after maybe 2 weeks exactly, he became very good with the examples. Yeah, but for me, really, I'm focusing on the fundamental things, what you have to understand behind these icons. But if you go to the help, you just go to the help, if you can show them now all of these steps, how we can follow getting this step.
Documentation because they can find it.
Okay.
Unfortunately, it's not installed.
That is not installed.
Yeah. If you completely install
you have the
the
CD
software,
or the-
yes.
Yeah.
There's another
Okay.
part here, documentation. You can follow the documentation.
Oh, one icon missing there.
Yes.
One machine.
Normally there is 2 DVD or 2 CD for Abaqus.
Oh.
First CD is the
This.
software. Second one is documentation.
Oh, okay. So needs to install
Yeah, you
documentation
have to
also.
install, so you can follow each step. Okay. Okay, so yeah, we want to give you a small example now, just the extrusion, extrusion of the aluminium rod from 30 millimeter to 5 millimeter. That's all. The extrusion. Yeah, extrusion. Yeah. So just to start a new one.
Siapa MJ Zahab? MJ Zahab tu. Muhammad Zahab. Muhammad Zahab.
Oh, yang tu.
So I simulate all the process,
Oh.
extrusion process.
Yeah, this is just so they can share with you now. So the problem is what I mean extrusion of aluminium pellet from 30 centimeter to 5 centimeter. From 30 centimeter to 5 centimeter. So the first step now, what we have to think about. This is the software, this is the wood, you can work very good in Abaqus. And now, just what would be the first step?
Then two parts, right? One is the one that extrude, and the one is die.
So we have two parts, two or three.
Extrusion by die, one die.
Okay, then yeah, we have die.
And then the roll, the cylinder.
So die, yeah, and the container, there can be all one part. Die and the container can be one part. And the billet, this is the second part. Then we have two parts. Okay? Okay. Do we need model reduction?
Model reduction.
Yes. It is a cylinder. A cylinder, a billet, cylindrical. And we are going to be extruded to 5 centimeter. So we have symmetry. Then we can reduce even the section to become half model. Half model. Okay. So this is the first part. So now we are going to do the die, half die, and half pellet. Okay. Just choose a very simple die.
Okay, first we are going to part and create our die. As you know, our die is undeformable. Actually deformed, but we assume here undeformable. So we take discrete rigid as a die, and
So you will work as a 3D. You prefer 3D because how often you choose 2D or if you choose axisymmetry? It is difficult if you choose 2D.
for interaction you have problem.
We have a problem.
Yes, but 3D, yeah.
Interaction.
So you will solve it as a complete 3D or half 3D.
We can take each of them if prefer.
Okay, then
In
half
3D,
model.
half model we need a extra boundary condition on part. Increase a little bit computation time. But for full,
For full, it is easy for you.
easy and also for
It's
some.
easy. Okay, then yeah, take 3D.
Okay, die discrete rigid, and here I'm going to take shell. Why shell? Because in shell we need we can increase our mesh, our number of the elements, and the computation time also decreases. We taking shell.
So it will be as a surface. So the die surface will be as a shell.
Yes, die surface will be as shell. And the will depend on your how can I say your designing ability. You can take any of them. Here for die, I think revolution is more easier than other types. And approximate size 400. Continue. As you can see now, we have an axis here, axis of
We have
revolution.
300, the end dimension. Okay, so you can change dimension.
We have also angle. orbit is, diameter is 30
30
something
millimeter.
millimeter.
30 centimeters, and it is 300 millimeter.
So very huge. Above that, because we have a revolution after that.
This is a complete, not half section. Here he is going to the whole model because it is easy for him and for Abaqus. No, minus.
So 5 centimeter in
Yeah, 50 millimeter.
Ada ke soalan?
So we will revolve this, we will revolve around y-axis.
Oh,
This is by line, yeah?
yes.
Okay.
You should remove all the pages because in the mesh part and simulation these sections will make error for you. So here it will reduce for that part.
Five?
Five,
I think it's 5 or what?
one person.
Let's take it 5. No.
Also we have another.
Maybe I take it 5 or just take it 10.
What is the height of the part?
Height of what?
Height of part, yes.
Yeah, so we will start the billet as a cylinder. Yeah, not to start from the guy, but as a cylinder, starting from here, starting from here, and I think the height, okay, as 100. Okay.
Choosing this axis is also very important because of the assembly module. Because we are going to assemble our model. First I'm going to fix this one. Coincidence. The color also in the sketch show the constraint on the part. When it's green, it means it's fully constrained, and that's okay. If it turns to the purple, it means you have an error in your constraint. When it's yellow, it means you don't have enough constraint. That's not important always change color to the green, but it's important to take all of them away from purple. should take a center line because I take another axis. Now it's necessary to take center line. This one, the angle of the rotation is 90. We should change it to 360. Okay. Now we have our die. You can see the die here. As you can see here, we have just shape. When you take your part as a shell, another important point is taking a reference point for your part. In the tool, you can see we have a reference point. I choose that one, and you will see different points here. It's not important you take which of them because the part is discrete. You can take any of them. I take this point as a reference point. Our part now is completed. Now we are going to creating a second part. Second part is the billet. That's 3D, deformable.
Yeah, and that was the missing part in assembly. Yeah, when we make 4 parts, we should assign a reference point for each part. So we forgot that step. Okay, then we should assign a reference point for each part. So that's why we can assemble them. So that was the missing point. Okay, for each part we should assign a reference point.
Now we have a billet that's deformable, 3D. Again, the type extrusion is okay for this part. Continue. Here again, I'm going to take the axis.
Yeah, 100. 300 diameter, and the height, just make it 130. A cylindrical billet. Solid?
100.
Yeah, 120.
This is all the parts. And also we need a punch.
I think we can put punch or just to put a surface pressure. Put surface pressure on the back.
Surface pressure is okay, but surface pressure because apply on the deformable part,
Yes.
it again increases computational time too much. If we
It is better to
yeah.
take punch.
Yes, if we take punch and give a reference point, we can choose different kind of loading. For example, you can take velocity,
You can take pressure.
pressure, or anything you want.
Okay. So we need another part, 3 part.
The punch,
But the end mark here we can put just surface pressure on the back.
I will define punch as a surface pressure.
Okay.
It's punch. Discrete rigid, shell, revolution. Also here is okay for this one.
So for the deformable body, do you need to assign reference point? Yeah, only for the
For rigid, yes. For deformable now, I am going to assign a dotted plane because it's easier for me. So,
300.
we have revolution.
Yeah, okay. And the height just to take a shape. You choose shape.
Yes, I'm pretty sure.
I think you need also to take this fillet.
Dia memang betul lah.
If you skip this one, yeah, it will.
Dia buat
In mesh
laju.
generation, sometimes we have
Yeah.
problem for the
So take it small, take it one, because normally this should be very small. So do it up to the assembly only, and you can continue that one at home, okay? Until the missing point assembly.
I'll take second axis again because of this simple scheme. This is our patch. Again, we need a reference point. Any of the points. Okay, for example, I'm going to take this point as a reference point. Here you can see our fillet,
One.
punch, and
Die.
I'm going to rename this one the die. Okay. Now our three parties. For simplicity in assembly, we need also define datum plane for this part. Here you can define datum for your part. It's possible without datum plane, but with taking the axial plane, your assembly will be much more easier, and also your interactions. Offset from principal plane. You can see the principal plane here, x, y, z, and xz. This one I take yz, and we need also this plane, xz. These two planes will help us to assemble it more easier. After part we have a property.
Yeah, just to skip this one, just to go down to the assembly.
The assembly you need to call your parts. It's not important you bring which of them first. You bring that first. Again, important point is dependent mesh on part. Okay, this is our first part. After that, I will do fillet. Okay. Now we need to make these two one coaxial. In constraint we have coaxial. For coaxial you need to take two cylindrical surface. First surface and second surface. Okay. Now these two part has a little bit for simplicity in assembly also we need to define datum plane for the die to control the position of the beam. I back to the part and die, and for this one also I'm going to take datum plane and principle. Now we need x set. Take x set and that's back to the assembly. One of the problem in the Abaqus is now you cannot recognize which plane belong to which part. From view, assembly display option. In instance, you can hide and unhide your part for easy assembly. Now I'm going to unhide the die. Apply. have just my billet. In constraint, face to face, I take first surface, unhide my billet and hide my billet and unhide my die, apply, and take display. Okay, as you can see, the vector is, so we need to take a minus. Here also you can control your assembly in different sections. You can see this is our billet and this is our die. I cut it from half. Now our first part is okay. Now we need to pull our punch. Again in view, you can see it makes all of it. I unhide our billet. First we are going to make it coaxial, in constraint, coaxial. Take first cylindrical surface, hide this one, unhide die, apply, take this one, okay. Now we need to unhide our punch, second constraint, first face, billet, second one. You see the direction is different, we should flip one of them, okay, and Z.
This is under interaction. Is under interaction or just for assembly?
Yes.
But we need another step for interaction.
When we assemble completely here, we don't need for assembly again. But for giving interaction properties, yes, we need follow again this one.
But we already made it assembly and interaction together.
Not interaction. We have another option for the interactions. After assembly, we have a step. After that, we have interactions.
Because in interaction also we have to follow
Yes.
making surfaces.
Now assembly completed. You can see the upper section. This is the die, this is the billet, this is the punch. Next module is step. We have a initial as a default. Here it's important to take dynamic explicit.
Yeah, okay, we'll just skip this step. So for
Interaction.
just to go for interaction, because this is the most difficult steps. The interaction and the assembly and assign.
Interaction. We have three parts here. Interaction between billet and die, interaction between billet and punch, because punch and die is discrete rigid, we don't need to define any interaction between punch and die. Here I am going to create my first interaction. Great. Here you can see different kind of interactions. As we are going to select explicit step. So here is important to take explicit one or general contact. General contact is not accurate enough for this process like extrusion. Just if you have, for example, two parts and you have bending, that's okay. But for this one, surface to surface contact is very important to take. So continue. And as you can see here, select the first surface. Again, I am going to take a assembly display option. In interaction, we have two different surfaces, master surface and slave surface. Normally, we take a discrete rigid as a master surface. This is my die. I take all the part and done. You can see here we have two different surfaces, brown and purple. We need internal interaction, so that's important to take here. Now you can see the message, choose the second surface type. That's surface on what? On billet. So I'll hide the billet. All the part is in interaction with the punch. Now we have edit interactions. You see here, first surface picked already, second surface picked already. Here you have two different kind of mechanical constant formulation, kinematic and penalty. Kinematic is more accurate than penalty, but the computational time for kinematic is too high. Penalty is okay for our simulation. Another sliding formulation, you can refer to the documentation to see which of them is okay. Finite sliding for metal forming, always advise the Abaqus. For contact interaction properties, you need to create contact interaction properties. We are going to create contact interaction property 1, continue. We have another window here. In mechanical, our contact is just mechanical here. You can see here different kind of mechanical interactions with a tangential behavior. You can see here different formulation, frictionless, penalty, kinematic, exponential decay, and another one. For metal forming, normally we take penalty one. Take penalty. Here you can see the friction of coefficients. That's depending on your data. Here we are going to take it as a 0.2. And also for sticking friction, if you want to define sticking friction, you can define your shear stress here. Here you can see it defined as a non-limit. You can specify this one according to your yield stress, and by dividing by radical 3 if you are going to use landmines, or dividing by 2 if you are going to use Tresca. Now we take it as a non-limit, and that's okay. You can see here our first interaction defined here, okay, and you can see the squares on these two parts. It means these two parts correctly interacted together. Now we have second interaction between punch and billet. So I hide the die, apply, create our, again, I open this one, create a second interaction, interaction 2.
I think you have to make a surface set for the billet first. But I mean, create surfaces for the billet. We have one surface, that's cylindrical, one bottom and one top.
Automatically, so for the formal part, define the outer surface as a
because here you selected the whole surfaces to be interacted with the die. Although we have only two surfaces will be interacted.
Yes.
The outer and
up and down. Yes.
No,
the internal
outer one and the top.
Yeah.
And the,
yes. If we have a part, so here I can show you.
okay.
In continue. Here you can select the first surface. first surface here is punch, because that's my master surface.
This will be
No,
master.
Yes, master. And that's a pro. For second surface here.
Yeah.
As you can see here we have a surface. It's automatically yes. Take by the company. So I take. We can also take node region, but we are going to take surface. And here also you have another options. Take all the surface. Again, we should adjust time. Interaction properties previously defined. If your friction coefficient is different between punch and
Yeah, for surface here, the wood, what I mean, all the billet here has been chosen as one surface.
no, so each surface considered individually.
Yeah, but yeah, with the orientation of each surface, because now I want to change the orientation on the surface of the billet with the surface of the bunch.
No, so we don't need to take orientation. Because here our contact is isotropic. Yes, if we take anisotropic contact properties, yes, we need orientation. But now we don't need to take any orientation. Interaction now is completed, you can see. Here we have just inertia. Why? Because I pass a step module. If you create your step here, for example, as a explicit dynamic, continue, okay. In the interaction, you can see it's automatically propagated for the step 1. If you have 2, 3, any other step, you can here take or, for example, deactivate your step. For example, in step 1 you have interaction, but in step 2 you don't have interaction. You can deactivate the second interaction here. And interaction here completed.
Okay, yeah, until you stop because now it is. Yeah, I'm sure. Yeah, when you go home after 1 hour, you will forget all of this. Really, I'm sure. So the best way really is just to download 2 examples or 3 examples and follow the steps one by one. Even for me, I know, and after that, after 1 month, I forget, and then it is better to download the documents and choose 1 or 3 examples and before.